Okay, the last lesson in this little series on circular motion is simply relating some of the ideas that we've looked at into things that happen on roads with cars going over hills and around bends. The main reason for doing this is just to give you an idea of some of the context that the exam questions could be set in. Okay, if we look at over the top of a hill, little simple diagram over here, we've got a car going over a humpback bridge. It's quite a perfect humpback bridge, but we'll use the idea that it is a perfect circle. So it's a car of mass m travelling at a speed v over the top of a hill with a radius of curvature r. So if we just label up this diagram, there's the velocity. The weight of that car is mass times gravity, and the support force of the hill, the reaction force, is in the opposite direction to gravity, so it's upwards, there it is. And finally we've just got the radius of the curvature there. At the top of the hill, the support force of the hill is in the opposite direction of the car's weight, as shown by the diagram. So if we say the car's moving in circular motion, the centripetal force, the resultant force, must be the difference between these two forces. So we've got the force of gravity, mg. In the opposite direction, we've got the support force, so mg minus s, and that lot must equal the resultant force, which is mv squared over r, which is the centripetal force. At a certain speed, if we think about this, if that car goes too fast, it's going to lose contact with the road. Now, if it loses contact with the road, S in the equation we've just looked at here, S would become 0. So if we set S to be 0 in this equation, we end up with mg equals mv squared over r. You can see that the masses would cancel, so we end up with g equals v squared over r. Simply rearranging this, we can say v squared equals gr, so v equals root gr. So you can find the speed that the car would leave the road by simply knowing the radius of the curve, and that equation, v equals root gr, gives you the speed that the vehicle would lose contact with the road. And notice it's got nothing to do with the mass, which is quite surprising at first. So if we do a little quick example, a vehicle of mass 1200 kilograms passes over a bridge with a radius of 15 meters at a speed of 10 meters per second. Calculate first of all the centripetal acceleration of the vehicle on the bridge. Okay, dead easy. We've got a formula from last time. Centripetal acceleration is v squared over r. If we do 10 squared, velocity divided by the radius of 15, we end up with an answer of 6.67 meters per second squared for the acceleration. Question 2, what's the support force when at the top? Well, if we rearrange this equation to give S equals mg minus mv squared over r, just rearrange that to give S equals mg minus mv squared over r. If I put in my values of mg, v and r, I end up with a support force of approximately 3,772 newtons. And finally, the maximum speed without the vehicle leaving the road, well, we can use our quite clever little equation of v equals root gr to give us the square root of 9.81 times the radius of 15, gives us an answer of about 12.1 meters per second. Okay, another little one here around the bend. If we imagine this car's going around a bend, again it's got a mass of m and it's travelling at a speed v with a circle of radius r. If we label up, there's friction towards the centre of the circle. That's what's providing this centripetal force, is the friction between the road and the tyres. It's got a velocity and the car's got a mass of m. So as we've said, the centripetal force is provided by the frictional force between the tyres and the road. This is F equals mv squared over r. Now, for it not to skid, the friction must be less than a limiting value, so let's just call that F0, which is the frictional value of the surface, and the speed must be less than a certain value, and we'll call that V0. So this is for no skidding to occur. So we can use this to find like our maximum speeds or our maximum friction of the surface. So if we just look at a question, the maximum speed for no skidding, so this is our VO, the maximum speed for no skidding of a 750 kilogram vehicle on a roundabout of radius 20 metres is 9 metres per second. So this car, whatever it is at 750 kilograms, can go 9 metres per second in a 20 metre radius without skidding. Let's do part one, calculate the centripetal acceleration. That's A equals V squared over R again. So we've got 9 squared divided by the radius of 20 to give an answer of 4.05 metres per second squared. The centripetal force on the vehicle when moving at this speed, well, the centripetal force is F equals mv squared over r, or we can just take our last answer and multiply it by the mass. If we do that, we get an answer of 3,038 newtons. Now, just in part three, the limiting force of friction if the car skids at 16 metres per second. So here we've got the car actually skids at 16 metres per second, so this is our value for VO. So we want to find the limiting friction, this value of FO. So we just need to use mv squared over r again, but we're using v squared of 16 metres per second. If we put 16 metres per second squared divided by the radius times by the mass, we get a value of 9,600 newtons. So on that particular surface, the limiting force of friction is 9,600 newtons. So what could we do to increase this maximum speed? Well, obviously you could change the surface to make it have a higher limiting friction value, or you've got to think about what could we do to the vehicle itself. So we could decrease the mass to make the centripetal force less, or we could increase the radius that it goes at. If we increase the radius, we would be able to go much faster.